So I remember we completed this handout number 4, chapter number 3, handout number 4. We completed last time. Okay, so we discussed the differentiation of or derivative of composite functions. Okay, so that was our last topic. So the proof is not necessary, but you must know this theorem. Okay, you must know this theorem. Under this, there are three types of three things. One is what will be the derivative of function phi if f and g are differentiable at x naught and y naught respectively. Then if phi is differentiable at x naught and g is differentiable at y naught, and if y dash y naught not equal to 0, then what will be the derivative of fx naught? And similarly, phi is differentiable at x naught, f is differentiable at x naught, and f dash x naught is not equal to 0, then what will be the derivative of g at y naught? So these kind of things we did. Also, we discussed one example. Okay, so actually, without using the first principle, we are using this composite function, composite rule or composition rule to find the derivative of the function ln x. Okay, so we discussed this example with the last class. This handout is over. Okay, so I have uploaded the recordings of the last class. Those who missed the last class, you can, I have already shared the link. Okay, already I have shared the link. So if you go to that Google Drive, you can find all the previous recordings. Okay, so please, if you have missed the lectures, please go through the respective recording and try to understand. If you have any doubts, you can ask me anytime. Okay, even once the faculty opens, I will be there, so you can come and ask me your doubts. Okay, so I close this handout. We don't want this. Right now, we are moving to our last handout, which is there are some important theorems. We are going to discuss some theorems here. So proofs of these theorems, stating these theorems are important. Definitely, you will get some questions from this handout, in the sense that you will not get direct questions, but these are theorems, no? So most of this handout, most of the things are theorems. So examples also based on the theorems. Therefore, theorems, we can't change it, no? So you must know how to state the theorem and how to prove the theorem and how to apply the theorem. Okay, all these three things you must know. One is stating the theorem. Stating means writing the theorem. So when you write the theorem, you must include all the conditions. If you miss even a single word, okay, important, you can write the theorem in your own words, no problem. But if you miss any conditions or any other important things in the theorem, you will be given 0 marks. So first thing is you must know how to state the theorem. Second one, prove. How to prove the theorem, proving. Third thing, applying the theorem. Okay, sometime we will ask only stating. Sometime we will ask you to state and prove. So in that case, you must know. There are a few theorems, but you don't need to know all the theorems. I will mention 2 or 3 theorems. Okay, 2 or 3 theorems. All these theorems, proofs and statement also important. Right. So first, we'll have a definition of what is relative maxima and minima. Relative maxima and minima. Okay, maxima mean maximum, minima mean minimum. So this is the plural form of maximum and minimum. Plural form of maximum and minimum. And relative maxima, minima, there is another word. We call it as the local maxima and local minima. Or relative, some textbook uses the word, some textbook use the word relative, some textbook use the word local. Okay, so they are similar, relative or local maxima and minima, right? So let's try to understand what is relative maxima and local and relative minima, right? A real valued function f has a relative maximum at x naught if f of x naught is greater than or equal to fx for all x in some open interval containing x naught. So this is the definition for relative maximum. Okay, relative maximum. Similar definition for relative minimum. A real valued function. So you have, these are important words. A real valued function. F has relative minimum at x naught if f of x naught is less than or equal to f of x for all x in some open interval containing x naught. Okay, let's try to understand what does it mean actually. Say we have a function. Okay, we have a function. Say for an example, look at here. Say you have a function like this. Say this is your function fx. Okay, this is your function fx. Okay, now take a point x naught. So we have the point x naught here. Right? You just consider open interval containing this x naught. Say for an example, say delta is a positive number. Say delta is a positive number. We just consider an open interval like this. X naught minus delta, comma, x naught plus delta. So this is an open interval containing x naught because x naught definitely will belong to this interval. Okay, x naught definitely will belong to x naught. Now, in this interval, say for an example, this is your point x naught minus delta. Okay. And this is your point, say for an example, x naught plus delta. Now, in this interval, you compare this one. This is your interval. Okay. Now, this is your interval. So, in this interval, what is happening? Now, if you compare fx naught, and fx. Okay, fx naught. So, now you look at here. So, fx means all other value in this region. Okay, this is our fx naught. This is our fx naught. So now if you look at here, so in this interval, in this range, look at here. So here, this is our fx naught. So what is happening here? Fx naught is always greater than or equal to fx. Fx naught is always greater than or equal to fx in this range, in this interval. So if you have such a interval, if you have such an open interval containing x naught in which fx naught is greater than or equal to fx, then we say that what? F has a relative maximum. F has a relative maximum. So the opposite is what? Relative minimum. The similar way, if there is a point, okay, if there is an open interval, containing x naught in which fx naught is less than or equal to fx for all x in this interval. Look at here. So we are considering for all x in this interval. Which interval? This interval. Which interval? X naught minus delta, comma, x naught plus. So if you choose whatever the point, in this interval, okay, if we choose whatever the point in this interval, okay, so in this interval, okay, fx will be always less than or equal to fx naught in this interval. Then we say that this point is a maximum point. This point is the maximum point. So this is called the relative maximum. Why we are saying relative maximum? I will come to that later. So we are saying that this is the relative maximum. Similarly, we can have the similar discussion for relative minimum. So relative minimum mean what? Say for an example, this is the point x naught, and if you have an interval, say you have an interval, open interval x naught minus delta, comma x naught plus delta. This point must definitely, this interval will contain the point x naught, where delta is a positive number. Okay, so in this interval, so if you mark this x naught minus delta, say for an example, this will be x naught minus delta. And here, say for an example, this is x naught plus delta. So you have such a delta. You have such a delta such that what? F of x naught is less than or equal to f of x for all x in that interval. Say for an example, if we say this is equal to I, if we say this interval is equal to I for all x is in this interval. So look at here. So this is the minimum point. This is our f of x naught. Okay. So here this is the maximum. So in this interval, okay, look at here. So this is the lowest point. This is lowest. So this is called the relative minimum. This is called the relative minimum. So that is what here they have discussed. Okay. So f of x naught is less than or equal to this one. Now there are three examples here. Look at here. So here there is one point, x1. So look at now, x1 is actually what? It is a relative, it's a relative minima. Why we are saying it's a relative minima? Because if you have a open ball, are you all studying matrix space? No? Are you studying matrix space these days? Hello? Are you studying matrix space? Right. So in matrix space, you would have discussed open ball. Okay, open ball. So in two-dimensional, it's actually open interval. In three-dimensional, actually it will be a ball. So now you will see here. So you see here, if you take this interval, say for example, you can find an interval where in this interval, f of x1, okay, f of x1 always less than or equal to f of x. So definitely you can find an interval. You can find the interval. Similarly, here also you can find another thing. So x1 is also minima, x2 is also minima. So actually, that is why we are saying relative minima. Relative minima mean what? Relatively, it's a minimum. So now if you compare with the relative to the nearest point, if you take the nearest region, this is the relatively minimum one. If you take the nearest points, here this is the relatively nearest one, isn't it? So now if you look at the entire function, if you look at the entire graph, actually x2 is the minimum one. X2 is the global minimum. We say this as an absolute minimum. But x1 is also said to be minima. Why? Because it is a relatively the minimum one. Similarly, here also it's a relatively minimum one. Now, if you look at the second figure, here definitely you can find an interval. In this interval, this point, the point x1 is the maximum one. Definitely you can have an open interval. You can definitely construct an open interval. Okay, in this open interval, okay, this open interval should be in the region. Now your domain is what? Your domain is actually a comma b, no? So that is the domain of the function. So the open interval must be in this domain. It should not go outside. Okay, so x1 is definitely this interval. You can find an interval such that x1, f of x1 is what? Greater than or equal to f of x. F of x1 is greater than or equal to f of x for all x in this region. For all x in this region. Okay, first. But now if you look at the third figure, here there is no any relative extrema. Extrema means common name for minima and maxima. Extrema means common name for minima and maxima. That means that there is no relative maxima or minima. Extrema means common name for minima and maxima. Now, why we don't have a relative minima or maxima? Why? Because if we choose a point here, okay, if we choose a point here, okay, so you cannot find a interval, and you can't say for an example, this is your x1. Then you cannot find an interval in which f of x1 is greater than or equal to f of x for all x in this interval. You cannot find it here. You cannot find, because if you find such an interval, then there will be another point. There will be another point which will be less than that one. Which will be greater than that one. For example, if this is your x naught, x1, the point x1, then if you construct a open interval like this, now you see there is another point here. There is another point here which is greater than x1. That is greater than x1, isn't it? Say this is your point x1. Then this is your point x1 minus delta. And if this is your point x1 plus delta, then if you say that this x1 is the relative maxima, then what about this point? That one is even greater than x1. And what about this point? That one is even greater than x1, f of x1, isn't it? Therefore, in this graph, you cannot find such a relative maxima or minima. That is why it says that there is no any relative extrema in this open interval a comma b. Now, what about this point? What about this point? I'm asking just, what can you say about this point? This point cannot be a relative one, because why? Relative maxima or minima. The endpoints cannot be a relative maxima or minima. Why is that? Because we cannot have a open interval containing this one. Say for an example, you cannot have an open interval containing, say this side you have no problem, but this side you don't have any points. You don't have any points here, because B is the end point of the interval. So here there is no value. You have only one side. Therefore, the endpoints cannot be relative maxima or minima. You have to understand that one. The endpoints of the interval. You can't have the relative maxima or minima at the endpoint. So relative minima and maxima, they should be within the domain. That means that they should be within the things. Okay. So these are actually definitions. Now absolute maxima and absolute minima mean, okay, absolute maxima and absolute minima mean here we are talking as open interval. Here we are talking an open interval. Okay, here we are talking the domain. Domain mean what? Say for an example, say this is our A, sorry. This is the point A, and this is the point B, and this is our function. Okay, this is our function for an example. It's a smooth function. Now, if you look at here, say this is x naught, then throughout this region, fx naught is what? Less than or equal to fx for all x belongs to the domain. In this case, we say that function has an absolute minima. Okay, absolute minima means that is the minimum over the domain. Absolute minima means minimum over the domain. Relative minima means you just consider only the neighborhood of that particular point. If that is the minimum value in that neighborhood, then we say that it's a relative minima. Similarly, relative maxima. Okay, so that is the definition. So absolute maxima and absolute minima, that is local, absolute minima and things. There is another name for this one, global maxima and global minima. There is another name is global maxima, okay, local, global. That is another name for absolute maxima. So when we say a function has absolute maxima, a real valued function f has an absolute maximum at x naught if f of x naught is greater than f of x for all x in the domain. Okay, if you are considering the domain, okay, in that domain, if x naught is the f of x naught is the maximum, then we say that it's an absolute maximum. Now, for example, here, look at here, there's a picture. In this picture, this point is actually a relative minima. Why? This point is not an absolute minima. Sorry, absolute maxima. Why? It's actually a relative maxima. Because why? If you look at the entire domain, okay, there is another point here which is greater than that one. There is another point here that is which is greater than this one. Okay, so actually, so this is actually, now if you compare this picture, okay, in this domain, this is the highest value. This is the highest value. So this is actually absolute maximum. And if you look at the minimum, and this is the least one. So this is absolute minimum. But what about these two pictures? What about these two pictures? What about these two pictures? These actually absolute maximum, sorry, relative maximum, and this is also relative maximum. This is actually relative minimum. Okay, so these three things, the red color one, this is actually relative maximum. This is relative maximum. This orange color one is the relative minimum. Okay, this maroon color one is the absolute maximum. This green color is the absolute minimum. So absolute maximum, absolute minimum can happen at the endpoints because we are taking the domain. So here we are not talking about the open interval. Here we are not talking about the open interval. We are considering in the domain. So this the endpoint is included in the domain. No? The point actually our domain is what? A comma B. So f of b now in for this picture, actually what? F of b is greater than or equal to f of x for all x belongs to the interval. So therefore, f of b is actually the absolute maximum. Absolute maximum. Okay, absolute maximum. So you have to note it that absolute maximum or absolute minimum can happen at the endpoints, but relative maxima or relative minima, in other words, local maxima or local minima, cannot be at the endpoints. Do you understand this one? Do you understand the meaning of difference of absolute maximum and the relative maximum and those kind of things, students? Hello? Do you understand? What about others? Only 77 understood. Quickly tell me, we want to finish this handout today itself. What about others? Okay, anyway, right. So another one. So this is another theorem. This is called the Fermat's theorem. Okay. So actually, this is also one of the important one, but proof is not necessary. Proof is not necessary, but this is very useful one. Okay. let's try to proof is given here, but proof is not necessary. I will tell you for which theorem proof is necessary. Okay, for this theorem, proof is not necessary, though the proof is given here. Right, let's quickly try to understand what does Fermat's theorem state. Suppose f is a function from a to b to r, and suppose f has either local maximum or local minimum at x naught. Look at here, local maximum or local minimum at x naught. X naught belongs to a comma b. Okay, whenever we talk about the local maximum or local minimum, actually we consider in the open interval. Though the function is defined from the closed interval a to b, the local maximum and local minimum only be in open interval a comma b. If f is differentiable at x naught, then f dash x naught is 0. So what does it say? What does it say? Fermat's theorem says Fermat's theorem says, so we have a function f from a to b to r. F has local maxima or local minimum. Relative maxima or relative minimum, both are the same. At x naught, and f is differentiable. We know the meaning of differentiability. At x naught, then f dash x naught equals 0. So this is the Fermat's theorem. You all know these things. At the maximum or minimum, f dash is equal to 0. We all know that one. In order to find the maximum or minimum of a function, what do we normally do? We differentiate and equate to 0. Okay, so why is that? Because we know that if f has a local maximum or minimum at x naught, and f is differentiable. So these two conditions are important. So f has a local maximum or local minimum at x naught, and f is differentiable at x naught, then f dash x naught will be 0. Okay, so this is very important theorem. Actually, you don't want the proof. Okay, so proof is given here. Suppose f is local maximum at, now we are proving for one case. We are taking that f has a local maximum at x naught at a comma b. Okay, then now we are taking this way. Say for an example, so this is our function for an example. So we are considering only the, so this is point A and this is point B, and we are taking, this is our x naught. Okay. So this is our function of x. So now this is a local maximum. So we are taking that at x naught function has a local maximum. So then obviously we know that if h is a positive number, okay, so say this is the point x naught plus h. So this is fx naught, and this is f of x naught plus h. Okay, so f of x naught is what? F of x naught is always greater than f of x naught plus h. If h is positive. If h is negative, what is that? So if h is positive, if h is a positive number, look at here. If h is a positive, okay, then f of x naught, h is positive number, f of x naught plus h minus f of x naught over h, because f of x naught is always positive. Okay, so f of x naught is always greater than f of x naught plus h. Therefore, f of x naught plus h minus f of x naught will be negative number. So this part is negative. This part is positive. Therefore, always less than 0. If h is a negative number, if h is a negative number, then what will happen? If h is a negative number, then this part is negative. This part is negative. Then what about this one? H is negative number. H is negative mean f of x naught plus h minus f of x naught will be negative number. Why is that? Why it is negative? Can anybody tell me why is that negative? Why it is negative? If h is less than 0, why it is negative? This part is negative. F of x naught plus h minus f of x naught, why it will be negative now? Sorry, this one should be like this now. F of x naught, I'm sorry. The same x naught. These two are same x naught. Okay. So if h is negative, f of x naught plus h minus f of x naught will be negative number. Why is that? Can anybody tell me? Why this one is negative? It is a negative number. Because this is always negative. Look at here. F of x naught plus h1 is always negative. Okay. Whatever the thing. Okay. Here also, if h is negative means what? Look at here. H is negative mean what? X naught plus h mean somewhere here, no? So this is the point again. X naught plus h. If h is negative, x naught plus h mean before x naught. Okay. X naught plus h will be less than x naught if h is negative. So that means that before that one. Before that one. Okay. So that means somewhere here. So that is also, actually, this is always greater than this one. Therefore, always f of x naught plus h minus f of x naught less than or equal to 0. Okay, less than or equal to 0. That is why we are having this one less than or equal to 0. So this is negative. This is positive. Therefore, negative. This is negative. This is also negative. Therefore, positive. Okay. So from the elementary properties of the limit, okay. So this is actually what? This is actually what? Differentiation, no? Limit, if you take limit both sides, actually this is the definition of derivative at x naught. Similarly, this is the definition of x, h tends to 0. Here h tends to 0. So this is nothing but definition of differentiation. So that is less than or equal to 0. If it is less than, this is also less than or equal to 0. Therefore, this derivative, this limit part is between 0 and 0. Therefore, what we can conclude? If something is between, say for an example, a is less than or equal to 0 and greater than or equal to 0, what is the conclusion? A must be equal to 0. So that is what we are having here. Actually, this is what? This is what actually? This is nothing but f dash x naught. Similarly, this is what? This is also nothing but f dash x naught. So what we are finally having, f dash x naught is between 0 and 0. So that implies as f dash x naught is equal to 0. Okay. So here there is a remark. The previous theorem is not valid if x naught is a or b. Okay. So the previous theorem is not valid if x naught is a or b, because look at the theorem. If a local maximum at x naught belong to open interval. Okay, open interval. Because here there is an example. If we consider the function from 0 to 1 r such that fx is equal to x, then fx has maximum at 1. Fx has maximum at 1, but f dash x, x equal 1, is not equal to 0. This is not equal to 0 because actually according to the definition, f dash x naught should be equal to what? 0. Here look at what they are saying is, you take the function fx equal 1, fx equal f, fx equal x. Okay, fx equal x. Okay, so what is f dash x? F dash x is equal to 1 for all x. For all x in the region 0 to 1. Okay, function is defined from where to where? Function is defined from 0, 1 to r. Okay, so if I draw this function, it's like this. So this is the point 0 and this is the point 1. So what is the maximum of this function in this? What is the maximum of the function? So maximum of the function in this interval is what? F of 1. So maximum is attained. So at x equal 1. So if you observe this one, at x equal 1, f has maximum. F has maximum. But what? F dash 1. F dash 1 is what? Actually, fx is equal to 1. It's a constant function. Therefore, f dash x is also 1, which is not equal to 0. Which is not equal to 0. So you may think that according to the Fermat's theorem, if x naught is the maximum, x naught is the maximum or minimum, then f dash x naught should be 0. But we are getting here, we are getting what we are getting here. We are getting f dash 1 is equal to 1, which is not equal to 0. Therefore, Fermat's theorem wrong. No, it is not wrong, because the theorem says that if we have a maximum in this open interval. Okay, so if you have a maximum in the open interval 0, 1, actually we don't have any maximum or minimum in the open interval 0, 1. We don't have any local maximum or minimum in the open interval 0, 1. There is no any minimum or maximum in the open interval. Okay, therefore that is why Fermat's theorem is not applicable for this function, because this function does not have what? Local maximum or minimum. This function doesn't have local maximum or minimum, but the function has absolute maxima and absolute minima. Absolute maxima is 1, absolute minima is 0. Absolute maxima is 1, absolute minima is 0. But function does not have local maxima or local minima in this one. That is why Fermat's theorem is not applicable here, because Fermat's theorem says that if we have either local maxima or local minima, then only the Fermat's theorem is applicable. Then only Fermat's theorem is applicable. Now, like earlier one, look at here. As I told you, local maxima. Okay. Now, if you look at this function, as I explained earlier, this function actually doesn't have local minima. There is no any relative minima or maxima for this function, because but the function has minimum, absolute minimum at 1 and absolute maximum at A, absolute minimum at B and absolute maximum at A. Absolute maximum and absolute minimum are there, but function doesn't have relative maxima. So if the function doesn't have relative maxima or relative minima, then Fermat theorem is not applicable. Do you understand the idea, students? Do you understand the idea? Tell me whether you understand or not. So proof is not important, but you must know this one. Okay, so you have to be careful with all these wordings. Huh? Otherwise, there will be a problem. Right. So that is the remark. So try to understand the meaning of the remark. Now, the theorem, another theorem is extreme value theorem. Extreme value theorem. So this is one of the important theorem. But here again, the proof is not necessary. Proof is not given here. Okay, proof is not given here, but the theorem is important. Right. This theorem says that extreme value theorem states that if a real valued function f is continuous on the closed and bounded interval. So these wordings are important. Continuous on the closed and bounded interval a comma b, then f must attain a maximum and a minimum at each at least one. That is, there exists a number c and d in AB such that f of c greater than or equal to f of x greater than or equal to f of b for all x comma x belongs to a comma b. So what is the meaning of that one? So we'll talk about the extreme value theorem. We call it as the EVT. So we have a function. We have a function from closed bounded. Bounded mean what? Closed mean what? A comma b. This should be a like this one. AB should be included from R. Closed mean closed. Bounded mean what? A comma B must be a real number. A comma B must be a real number. That is the meaning of bounded one. Okay. So that is the meaning of bounded one. Bounded. Closed mean what? X is actually less than or equal to B. So this is called a closed. So this interval is bounded as well as closed. Okay. F is a function from A to B. Then it says that then F must attain. That means that there will be F must attain at least one maximum and at least one minimum in A comma B. So if the function is defined from A comma B to R, where it's a closed and bounded interval, then F must attain at least one maximum and one minimum. There can be more than one maximum, there can be more than one minimum, but at least there will be at least one maximum and there will be at least one minimum. This is here they are talking about the global maximum or absolute maximum and absolute minimum. Huh? Here they are not talking about the local maximum, local minimum. Okay, because we heard earlier we had an example where we don't have a maximum. Here it's actually a bounded interval. 0 to 1 is a bounded interval. It's a closed interval, but we said that there is no any local maxima or local minima for this function. But actually function has a absolute maxima and absolute minima. So here they are actually referring to any maxima or any minima. Okay, that means that we can consider it as a absolute maxima or absolute minima. Okay, you will have a maxima as well as minima, at least one minima, maxima, and one minima. Okay, so that is the meaning of that one. Say now, say the maxima happen, we are getting the maximum at x equals c. Maxima is occurred at x equals c. Then minima is occurred at x equal t. Then how we can write? How we can write? F of c will be greater than or equal to f of x will be greater than or equal to f of for all x belongs to a comma b. So this is what this EVT EVT means extreme value theorem says. The function is from bounded closed interval to R, then f must attain at least 1. So another condition is also there. I think it's a continuous function. That is also very important. There are three things. F is a continuous function. That is also important. Continuous function. So there are three conditions. This interval should be open and closed. Sorry, this interval should be bounded and closed. Function should be continuous function. Then f must attain at least one maxima and one minima. If we say when x equals c, the function attains the maximum, and when x equal d, the function attains the minimum, then you can write it f of c is always greater than or equal to f of x is always greater than or equal to f of d for all x this one. Okay, so that is what this extreme value theorem says. So simply, if you want to understand the extreme value theorem, if you have a continuous function from closed and bounded interval to real number, definitely there will be a maximum value. Function will have a maximum and function will have a minimum value. That is the thing. Okay, here also you can observe that. For an example, here it's a function, it's a bounded closed interval. Bounded closed interval. Fx equal x is a continuous function. There is no any break in this function. Therefore, definitely there is one maximum and there is one minimum. At least one maximum and one minimum. There can be more than one. There can be more than one. Definitely there will be one maximum and one minimum. That is what extreme value theorem says. Okay, right. So this theorem is useful when we have to prove the Rolle's theorem. So this theorem is important. This theorem is important. Proof is also important. So now we'll try to understand what does Rolle theorem states. So this is actually an informal one. We'll later have the formal one. So if they ask the Rolle's theorem, actually you have to write this one, not this one. This is actually the informal one. Informally, Rolle's theorem states that if the outputs of a differentiable function f are equal at the endpoints of an interval, then there must be an interior point C where f dash C is equal to 0. So what does it say is output means functional value. So we have a function. So it says that we have a function f from a comma b to r. A comma b to r, closed and bounded interval. There are some conditions. F is continuous on a comma b. Second one, f is differentiable on open interval a comma b. You have to be careful with these notations. Huh? Look at here. Continuity must be a comma b closed interval. Differentiability can be a comma b open interval. Third condition, f of a must be equal to f of b. That means that the functional value at the endpoints, a is the starting point, b is the end point of the interval. Okay, then it says that then there exists a point C belongs to the open interval a comma b such that f dash C equal to 0. F dash C is equal to 0. So this is what the Rolle's theorem says. If you have a function a to b to r which is continuous on closed interval a comma b, which is differentiable on open interval a comma b. Also, f of a equal, the functional value at a and b are equal, then the Rolle's theorem says that there will be a c in this interval such that f dash c equal to 0. Okay, so this is the statement of the Rolle's theorem. So now let's try to understand here. Look at here. There are different things. There exists c. So as I told you, there exists c. So there can be more than one c. There can be more than one c. So Rolle's theorem guarantees at least one c. There can be more than that one. Now let's try to understand from this figure before we formally have this thing. Before we formally. Now you look at here, we have a function. We have a function, which is a differentiable function, continuous function. Now look at f of a equal to f of b, isn't it? Here f of a equal to f of b. Then in between this a and b, there will be a point c where f dash c equal to 0. F dash c will be equal to 0. So f dash c means equal to 0 mean what? It will be parallel to, actually f dash x gives what? Normally f dash x gives what? Derivative of a function gives what? The slope of the tangent. Slope of the tangent of the function at x equal x. X equal x. Say for an example, f of x dash a means x equal a. Slope. Another name for slope is gradient. So f dash x normally derivative is what? Derivative is the gradient, no? Normally derivative is the gradient. So f dash c is equal to 0 mean what? The gradient is 0. So gradient is 0 mean what? It will be parallel to x-axis. Okay, so that means that there will be a point c. There will be a point c at which if you draw the gradient, that will be equal to 0. So that is the meaning of the Rolle's theorem. So now here, another possibility, look at here. Look at here, there is another possibility. Here also you look at f of a equal to f of b. F of a equal to f of b. Then it's a continuous function. It's a differentiable function. F of a equal to f of b. Then definitely in between a and b, there will be a point c where, okay, if you draw the tangent, then that tangent will be parallel to x-axis. Similarly, look at here. Okay, there is a function. This is actually our f of a. But again, that is same as f of b. F of a and f of b is same. F of a is equal to f of b. Then this is a continuous function. It's a smooth function. Therefore, it's a differentiable one. Therefore, between a and b, you have 2 points. Okay, at these 2 points, look at here. F dash c is equal to 0. F dash c1 is equal to 0. F dash c2 is equal to 0. So simply, this is what Rolle's theorem says. Rolle's theorem says that if a function satisfies 3 conditions, what are the conditions? F is differentiable, sorry, f is continuous on the closed interval a comma b. F is differentiable on the open interval a comma b. And f of a equal to f of b. That is, the functional value at the endpoints are equal. Then definitely there will be at least one point c such that at that point the derivative of the function will be equal to 0. So this is what Rolle's theorem says. So let's have the formal definition of Rolle's theorem. This is the statement. So this is what you have to write if they ask you in the final exam, right? Suppose f is a continuous function defined on closed and bounded interval a comma b. Okay, so these 3 words are important. Closed continuous function on where? Such that it is differentiable at every x belongs to a comma b, open interval a comma b. third condition, this is the first condition. Continuous on closed bounded interval. This is the first condition. Second condition, differentiable at every x belongs to a comma b. This is the second condition. Third condition, f of a equal to f of b. This is the third condition. Then there exists c belongs to where? This is also very important. If you write a comma b, that is wrong. You will be given 0 marks. Instead of writing open interval a comma b, if you write closed interval a comma b, you will be given 0 marks. So very, very important. There exists c belongs to a comma b such that at that c, the derivative of the function will be equal to 0. That means that at this point, if you draw the tangent to the function, that will be parallel to x-axis. So this is what the Rolle's theorem states. This is what the Rolle's theorem states. Let's try to prove this one, Rolle's theorem, quickly. We have that function, right? This is the proof. Proof is very simple. You can understand easily. Okay, right. So we have that f is continuous and on the closed and bounded interval a comma b. Look at here. F is continuous on the closed and bounded interval a comma b. Thus, f attains maximum value m and minimum value m on a comma b. So this statement is coming from where? Can anybody tell me? This statement is coming from where? Can anybody tell me where it is coming? From the definition, we are writing f is continuous on the closed and bounded interval a comma b. Then you can directly write this statement. Where this statement is coming from? Tell me quickly. Can anybody tell me where it is coming from? Yeah. So it is nothing but extreme value theorem. So there will be at least one maximum and there will be at least one minimum. That is what extreme value theorem says. So we are taking the maximum value as m and the minimum value as simple m. Actually, this is a functional value, not the x value. Huh? This is the functional value. This is the maximum functional value and this is the minimum functional value on a comma b. Now, there are two situations. One is that maximum is equal to minimum. You may think that can it happen? It can happen. When it can happen? When a function can have both maximum and minimum equal. Can you tell me when a function can have both maximum and minimum equal? You have a function like this. This is the interval a comma b. So we have a function like this. So when the maximum and the minimum of the function can be equal, when the maximum and the minimum of the function can be equal, can you tell me? If the maximum and the minimum of the function is equal, then the function should be a constant function. Maximum is also equal, minimum is also equal. Okay, so it says that, so first case number one, m is equal to simple m. That is maximum value equal to minimum one. Then f is a constant function. Maximum equal minimum means it cannot have a bends. It can be a straight line, which is parallel to x-axis. Then if it's a parallel to x-axis, then what is, say, fx is equal to constant function. Then we know that f dash x is equal to what? 0. Okay, so we can say that f dash x is equal to 0 for all x comma belongs to a comma b. Then you have many points. Actually, in this theorem, we are saying that there exists one point. There exists one point. But here, we can conclude that for all the point between a comma b, for any point c between this f dash c will be 0. So we are done. Because here for any point, here according to this theorem, we want to show that there exists a point, at least one point. But here we are finally concluding that for all c between this open interval a comma b, okay, any point, okay, any arbitrary point, it will be 0. So we are done. Now the second case is that m is not equal to m. So first case, there are only two possibilities. M is equal to m and m is not equal to capital M. Sorry, capital M is not equal to simple m. then at least one of MOM must be different from FA and FB. Can anybody tell me why is that? At least one of this one. We have capital M. This is the F maximum. We have simple M, which is equal to F minimum. Which is equal to F minimum. Okay, capital M is equal to F maximum, simple M is equal to F minimum. Then at least one of these must be different from FA and FB. At least one of these must be different from FA and M and FA and FB. Why is that? That means that one of these should not be equal to FA and FB. Why is that? Because, say for an example, capital M is equal to FA and simple M is equal to FB. Say for an example, capital M is equal to FA and simple M is equal to FB. Then what is that? Then what is that? Then in our condition, we have already there that FA equal to FB, FA equal to FB. Then this will imply capital M is equal to simple M. So this is a contradiction for our case. This is a contradiction. So in this case, actually we are considering M is not equal to M. M is not, capital M is not equal to M. So from this one, we can say that capital M, one of these should not be equal to F of A and F of B. Otherwise, it will contradict this condition. This condition. If you take capital M is equal to FA and FB, if you take capital M is equal to FA and FB, then capital simple M cannot be equal to FA and FB. Okay, so must be different from this one. So that is the reason. So without loss of generality, that means that one of this will be different from FA and FB. One of this will be different from FA and FB. So we'll, without losing the generality, we are going to say that a capital M is the one who is not equal to FA and FB. We are taking this one. Okay, if you want, you can take simple M also, no problem. So if you take one of these, the thing is same. Okay, therefore, without making more argument, we just take a capital M is not equal to FA and FB. Then what is happening? If capital M is not equal to FA and FB, what is happening then? Then there exists C belongs to A comma B such that M is equal to FC. Why is that? Why is that? Because this is the function. Say for an example, this is your M. This is the point. Okay, so this is your M. This is the point A. This is the point B. F of A is equal to F of B. F of A is equal to F of B. Then if M is not equal to F, M is not equal to this point or this point. M is not equal to this point or this point. Okay, M is not here. That means that what? That means that what? M is not equal to FA and MB means what? What is the meaning of this one? Can anybody tell me what is the meaning of this one? Maximum F max does not occur at x equal A or x equal B. Because why? We are saying, we are taking that M is not equal to FA and FB. So maximum is not occurring at A or B. Therefore, but M is clearly, according to the extreme value theorem, M is clearly the maximum value of the function. Therefore, but these are not the maximum points. So maximum is not occurring at A or B. Therefore, definitely what should happen? There is an internal point between A and B where F has a maximum. So F has a maximum at x equals C. There should be an internal point. There should be an internal point. But at the maximum, what is happening? Normally, according to this theorem, Fermat's theorem, according to Fermat's theorem, what? If you have a local maxima or if you have a local maximum, x naught, then f dash x naught is 0. F dash x naught is 0. Therefore, what is happening here? Actually, the C is in between this one. C is not an endpoint. Therefore, C will be a local. C is not an endpoint because C is between the point A and B. Therefore, F has a maximum at x equals C. Therefore, from the Fermat's theorem, we can say that f dash C is equal to 0. Okay, the proof is very simple. The proof is very, very, very simple if you understand. Okay, here we are actually using the Fermat's theorem. We are using the Fermat's theorem. Try to understand this. Okay, so this is the proof of this one. Proof, definitely I will ask for the exam. I will definitely ask the proof and the statement for the exam. Okay, so that is very important. Now there are some exercises we will try to understand this one. Okay, verify whether the function fx equals sin x is sin x in 0 to pi satisfy the conditions of Rolle's theorem, and hence find the C as prescribed by the theorem. So here they are asking us to verify this one. Here they are asking us to verify this one. So we have to verify whether the conditions are satisfied. What are the conditions? So here, first example, our function is given fx is equal to sin x. The range is 0 to pi. So we have to verify 3 conditions. First, you can write it. Definitely, if you draw the function, we have already even proved this one. F is obviously continuous. F is continuous on 0 comma pi. Again, we have proved that f is differentiable also. You can verify that f is differentiable. F is differentiable on this one. These 2 things, actually using the previous knowledge, chapter 1. This is actually chapter 1, chapter 3, sorry, chapter 3, second one. Continuity. This is actually chapter 3, third one, differentiability. Using those knowledge, you can verify this one. F is continuous on this one and F is different. When you write it, this is closed interval. When you write this, you must write it open interval. If you write it wrongly, marks will be deducted. Third condition, you have to check f of 0 equal to f of pi equal to 0. Sin 0 equals sin pi equals 0. Therefore, all 3 conditions are satisfied. Because this is a continuous function, since it's a smooth function, definitely it's a differentiable function. Therefore, all 3 conditions are satisfied. All 3 conditions for Rolle's theorem satisfied. Therefore, Rolle's theorem is applicable. Now they are asking us to find the C. So conclusion says what? There exists C belongs to A comma B. So here our A is 0 comma pi. There exists C belongs to open interval. You have to write carefully. This is open interval. C belongs to 0 comma pi such that f dash C is equal to 0. So now we are asking what is the value of C. If these three conditions are satisfied only, we are able to find C. Otherwise, we cannot find. So we know that f dash x is equal to cos x equal to 0. So then what is the value of C? So cos x equal to 0 means what? For which value x will be C? X will be this one. If x equal pi by 2, which is belongs to open interval 0 comma pi, then f dash pi by 2 is 0. Therefore, C is equal to. So that is the answer. So the examination, if you ask the question, first of all, you have to check all these three conditions. Otherwise, you will be, just if you find C, that is not enough. Do you understand this? Do you understand, students? Tell me whether you understand or not. So we'll discuss one more example. What about the second one? What about the second one? So the function is given fx is equal to mod of x, where the range is -1 comma +1. So first condition, obviously, if you draw this one, -1 to +1, actually it will be like this, no? So third condition satisfied. F of -1 equal to f of 1 equal to 1. So that is satisfied. First condition, it's a continuous function, you see. It's a continuous. F is continuous on -1 plus. Second one. Now, can you see any thing that is parallel? That is parallel. Can you draw a? If you draw the tangent to this function anywhere, do you think that it will be parallel to x-axis? So now, what can you say about the second condition? Can anybody tell me what can you say about this one? F is what? F is what? Quickly tell me. We have another, otherwise we can't finish it today. Already we have done similar things, similar in the sense that we discussed about this function. I told you this is one of the important function. F is what? F is what? Fx equal mod x is what? Fx equal mod x is what? Yeah, it is not differentiable. Not differentiable at x equals 0. Belongs to -1 comma 1. So there is one point, because according to this theorem, look at here, according to this theorem, it should be differentiable at every x belongs to a comma b. Even if it fails at one point, then we cannot apply this one. So it should be differentiable everywhere. So at x equals 0, it's not differential. Therefore, second condition fails. Second condition fails because one point is at one point it is not differentiable. At one point it is not differentiable. Therefore, in this open interval it is not differentiable. Therefore, second condition failed. Therefore, RT is not applicable. You cannot apply Rolle's theorem for this function. You cannot apply Rolle's theorem for this function. Okay, because you see, you cannot draw a parallel. If you draw a tangent to this function anywhere, it will be never be equal to parallel to x-axis. Okay, so you have to be careful with that. So you don't need to write these conditions. If you write only this condition, second one, that is enough for this exam. For this example, for this question, if you mention only the second one, which is not satisfying, then that is enough for saying that R is not applicable. Okay, so I let these two questions, question number 4 and question number 3. Okay, these two are important questions. Okay, please try. I will get a similar question for your final exam. Okay, please try example number 3 and example number 4. If you have any doubts, you can come and ask me. Okay, when faculty reopens, please come and ask me. Okay, I will explain this one. Okay, so think you can expand this as binomial because M and MB are positive integers. Therefore, think that one. So, okay, so check the conditions for the applicability of Rolle's theorem. Here, look at examine the validity of hypothesis. Hypothesis means condition. Hypothesis means condition, assumptions, and conclusions of the Rolle's theorem. So, conclusion is what? If the conditions are satisfied, there will be C. Okay, there will be a conclusion. So then they are asking us to find it. Okay, so that is the one. Now check this also. Okay, right. Now we are moving to another one. This is also very important. This is also very important. Proof is also important. Now it says that actually you can think this as a corollary to the Rolle's theorem. Rolle's theorem as a corollary. This is easy. Suppose f is a continuous function defined on closed and bounded interval. Look at this one. The same condition. Continuous function defined on closed and bounded interval a, comma b, such that f is such that it is differentiable at every x belongs to a, comma b. So the same condition which we require for Rolle's theorem. First one is closed and this one continuous, closed and bounded interval. The second, only the first two conditions. We don't want FA equal FB here. We don't want FA equal FB here. So this is the first condition. This is the second condition. Then it says that there exists C belongs to open interval. Again, open interval. Differentiability also at the open interval. Continuity at the closed interval. Look at here. You have to look at this one. Then there exists C belongs to AB such that f of B minus f of A equal to f dash C into B minus A. So let me explain it again here. So this is called the MVT. People normally write it as MVT, mean value theorem. Mean value theorem says that, okay, we have a function f from closed and bounded interval A comma B to R, which satisfy two conditions. One is f is continuous on opening closed interval A comma B, that means throughout the domain. The second condition, f is differentiable on A comma B open interval. Then there exists C. There may be more than one C. There exists C belongs to open interval A comma B. Open interval A comma B such that FB minus FA equal to F dash C into B minus C. So this is called the mean value theorem. So what does it mean actually? Just before we look into the proof, what does it mean? F of B mean what? F of B mean what? The functional value at x equal B. F of A mean what? Functional value at x equal A. Okay, so if you want, you can write this in this way also. F of B minus F of A over B minus A equal to F dash. So what is this? Can anybody tell me what is this? Say, if you have a function like this, so this is actually F of A. F of A. This is actually F of B. So, okay, F of B. So what is this one? F of A minus, sorry, F of B minus F of A. I'm sorry for this one. Yeah, F of B minus F of A. What do you mean by F of B? Can anybody tell me what is this? What is this factor? F of B minus F of A over B minus A is what? Not definition of derivative. We don't have X. This is something. What is this? F of B minus F of A over B minus A is what? Can anybody tell me what is this? F of B. So F of B is this. F of A is this. So F of B minus F of A means this distance. This is actually F of B minus F of A. B minus A means this distance. So what is this? This distance over this distance. What is that? The vertical distance over the horizontal distance. What is that? This is nothing. Okay, this is nothing. The slope of this line. Slope of the line connecting these two lines. The slope of this line. This is nothing. Slope of there is a two name for this line. This is called chord. Or sometimes we say that secant. Secant line. C-S-C-C-A-N-D. Secant. So slope of secant. So Rolle's theorem says that. Rolle's theorem says there is a C F dash equal to F dash. So Rolle's theorem says that if these two conditions are satisfied, try to understand what does Rolle's theorem says clearly. If these two conditions are satisfied, Rolle's theorem says that there is a point C between A and B such that F dash C means what? The tangent at C. The tangent at C will be equal to tangent, sorry, the slope of the tangent at C equal to, this is what actually? Slope of F at x equals C. So it says that if these two conditions are satisfied, Rolle's theorem says that there will be a point C. There will be a point C such that, okay, f dash C, that is the slope of f at x equals C, will be parallel to the slope of the secant line. So that is what the mean value theorem says. Here, look at here. This is slope of the chord. Chord, or another name is secant line. Secant. So it says that if these two conditions are satisfied, between A and B, there will be a point C such that if you draw the tangent, these two will be parallel. That is what it says. Do you understand this? Do you understand? First of all, tell me whether you understand what does it mean. Then we'll try to prove this one. Hello? Tell me whether you understood or not. Do you understand the geographical interpretation of a mean value theorem? What about others? Only 77. Hello? Others are sleeping. Whether you understand or not, tell me. Hello? What about others? So now we'll prove this one. So I define a function pi. Okay, I define a function pi in this way. So I'm defining this one. So where it is coming from? Nowhere. We are defining. We are just defining this function. Why we are defining? We are defining for some purpose. Defining, sorry. We are defining. We are defining a function pi like this. Fx minus fa minus fb minus fa over b minus a into x minus b. We are taking the same domain. X belongs to a comma b. Now, pi is continuous on a comma b and differentiable in a comma b. Why we can say differentiable in a comma b and continuous in a comma b? Because we have a function like this. F is continuous function. Fx is continuous function. This is a constant. Again, this is a polynomial function. X minus a is a polynomial linear function. Therefore, this is continuous. This is continuous. These are constant. Therefore, pi is continuous. Pi is differentiable. This is a polynomial function. Normally, polynomial functions are differentiable. Polynomial functions. Polynomial functions are always continuous and differentiable. You must know these things. Huh? So most of the time in real analysis, we use this one. You may have to write this one. Polynomial functions are always continuous. So x minus a is a linear function. It's a polynomial function of order 1. So it's a polynomial function. Already from the assumption, fx is continuous function. We are using the same fx. So this function pi is continuous and differentiable. So those two conditions are now satisfied. Continuous on a comma b, differentiable on a comma b. Again, if you substitute pi a, okay, if a instead of a, if you substitute pi a is equal to 0 because fa minus fa 0, a minus a is 0, therefore pi a is equal to 0. Similarly, if you substitute x equal b, this is actually function pi x. So if you substitute x equal a, then this becomes 0, and fb equal, again if you substitute b, again that is 0. So now we have three conditions. One is function is continuous, function is differentiable, the terminal values are equal, functional value at the terminal point a comma b are equal. So now what we can do, now three conditions are satisfied: continuity, differentiability, functional value at the endpoints are equal. So now what we can apply? Can anybody tell me what we can apply? This is our third condition. So can you remember these three conditions where we look at? So what you can say now? Yeah, that is actually Rolle's theorem. Then you can say that from the Rolle's theorem, you can say that there exists f dash x is equal to, okay, then by Rolle's theorem, you can say what? Then Rolle's theorem, you can say that there exists C belongs to, A comma B such that pi dash C is equal to 0. So actually pi dash x is equal to what? F dash x minus, because this if we differentiate this function, we are defining pi as fx minus fa minus fb minus fa over b minus a into x minus a. So if you derivate this one, this is equal to f dash x. This is a constant. Here this is a linear function. So that will be equal to, if you differentiate x, that is 1 time. So we get fb minus fa over b minus a. Okay. So this is the derivative. From the Rolle's theorem, but there exists C belongs to A comma B such that pi dash C is equal to. So then we are substituting here pi dash C equals 0 equal f dash C minus f of B minus f of A over B minus C. So if you equate this one and multiply, you will have f of B minus f of A is equal to f dash C into B minus. So that is the mean value here. Okay, so that is the mean value here. Do you understand this one, students? Do you understand this one? Tell me quickly. Hello, tell me whether you understand or not. So you must know how to define. So you have to remember this, how we are defining the function. We are defining for purpose such that continuous differentiable. In order to apply the Rolle's theorem, we have to define the function this way, where pi a equal pi b equal 0. Need not to be 0, but here they are equal and we are getting 0. It need not to be 0. So 0 is not significant here. It can be any number, because according to the Rolle's theorem, we don't want they have to be equal. If they are equal, only enough. But here we are showing that they are 0 also. So, okay, there is no any advantage over having this equal 0. Okay, right. Now there is an example here. This is a very good example. So similar question you will get for your exam. Now we are given fx equals square root of x over the interval 0, 9. Show that f satisfy the hypothesis of the mean value theorem, and therefore there exists at least one C belongs to this one such that yeah, so there exists this such that f dash C is equal to slope of the line connecting this one f0, f0 and this one. Okay, so let's do this one. We have the function fx is equal to square root of x. It is defined on the interval 0, 9. And actually, if you draw this one, it's like this. Sorry. Actually, this function is like this. If you draw the square root function, it's a smooth one. Sorry, I'm not good in drawing. Anyway, we'll have this one. So this is 3, sorry, 9. This is 0. And this will be 3. F of 9 is actually equal to 3. Now, now the question is this one. Question is, find the values of C guaranteed by the mean value theorem. Okay. First of all, we are asked to show that F satisfies the hypothesis. Okay. Right. So, if you look at this function, first thing is what? Obviously, okay, clearly, already we have proved this also. F is continuous on the domain 0, 9, and second one, F is differentiable on open interval 0, 9. How we are saying it is continuous? Okay, so actually you can use the definition. You can use the delta epsilon definition. So things here also you can use the definition. Okay, because actually now if you look at f dash x is what? F dash x is equal to what actually? Half into 1 over square root of x. But this is not differentiable at x equals 0. Because if we put x equals 0, actually this goes to infinity. Yeah, that is why we are having open interval. 0, 9. Okay, so that is, these things are very important. This is not differentiable at, but here it is differentiable over this one. This x exists. Okay, so this exists actually. So this is actually exist for all x belongs to open interval 0, 9. So those two conditions are satisfied. Therefore, MVT is applicable. Then there exists C belongs to A comma B. So our A comma B is actually 0, 9, such that f of 9 minus f of 0 is equal to f dash C into B minus A. So B is 9, C is A is 0. So F9 is what according to the one? 3. F0 is 0 equal to F dash C. So F dash X is this one. So we have half times square root of C. So if you simplify this, this is if you divide this 1 over 3, so 2 by 3, no? 2 by 3 is equal to 1 over square root of C. So if you square it both sides, you will get C is equal to, and if you square 9 by 4. So if you draw the, actually this is the one, this is the idea. Now we have the function like this. This is 3. Okay. So this is our secant line. Secant line connecting these 2 points. Okay. Let's make this. Sorry for that. This is our secant line. This is 9, 0, and 9 by 4. 9 by 4 means just somewhere here. So this is the point 9 by 4. And if you draw a line on this one, okay, this is actually 9 by 4 at this point. Sorry, I'm sorry. If you draw a line here, sorry, it will not cut the axis, it just go above. Okay, so please accept this line. Then this line and this line will be parallel. So what is that value? 9 by 4. Okay, so that is what here it is given. C is equal to 9 by 4. So we are trying to find it. So we are saying that we know that fx is continuous on a comma b, differentiable over there. Therefore, f satisfies the hypothesis of the mean value here. And there must exist c belongs to 0, 9 such that f dash c is equal to slope of the line connecting this one. This is actually what? f0, f0 mean what? This is the point. This is the coordinate connecting. This is the 0, f0. That's the coordinate of this point. And what is the coordinate of this point? 9, f9. So line connecting these two. That is what it says. Line connecting 0, f0 and 9, f9. To determine which value c guaranteed, first calculate the derivative. So derivative f dash x is equal to 1 over 2 square root of x. The slope of the line connecting 0, fd. That means that fb minus fa over b minus a is 1 over 3. Okay, so this should be equal to what? F dash c according to this one. So we are equating this one and we are getting this. So this is the idea. So this is the function fx equals square root of x. And this is the line, secant line. And we are trying to find the point where the tangent at that point will be parallel to the secant line. Okay. So these two will be there. So when x equal 9 by 4, this is your c value actually. C equal 9. You have found this value equal. If you draw a tangent, that tangent will be parallel to the secant line. So that is what it says. The slope of the tangent is equal same as the slope of this line. Do you understand this, students? Do you understand this one? Tell me whether you understand or not. So please try these two questions as a homework. Huh? Right. So we are moving to the last one. This is called the LaHospital's rules. So you might be familiar with these things without knowing actually it is LaHospital rules. Some people says okay, LaHospital's rules or LHospital's rules. So it says that this is actually about the limit. Actually, it's a first chapter. That is not the first chapter. Chapter number 3. First topic. But here derivative involves. That is why I haven't discussed this earlier. Now only I'm discussing. Now let's try to understand this and maybe another 50 minutes. I will finish the class by 10:35 or 40. Okay. So with that we complete our course. Let f and g be defined on open interval I and differentiable on I minus a. Okay. Need not to be defined on differentiable at a. If limit extends to a equal fx, limit gx extends to a equals 0 or plus or minus infinity. Okay. So you calculate the limit of the function fx, you calculate the limit of the function gx, both goes to 0 or both goes to plus infinity or minus infinity. Okay, and g dash x not equal to 0 for all x in I. with x not equal to I. That means that in this interval. Then limit f dash x over g dash x is, then limit fx over gx equal to f dash x over g dash x. So let's try to understand what is that. So now we are going to talk about the L'Hospital's. Have you heard about this one earlier in A level? Have you heard about this top idea, L'Hospital's rule? Have you discussed this idea in A level? Okay, you didn't know, right? Now, right. So this is one of the rules or one of the technique to evaluate limit of some complicated functions, normally rational functions. Say we want to evaluate the limit of the function fx over gx, rational type, not the rational type functions of this form when x tends to u. Okay, so we get something like this. So we want to evaluate this. So actually, if you substitute the value, we get either 0 by 0 indeterminate form, or we get plus infinity over plus infinity, plus or minus infinity over plus or minus infinity. These are called indeterminate form. Then, okay. So in order to evaluate this integral, this will be equal to limit f dash x over g dash x as x tends to u. Okay. So if you get the indeterminate form, only, you can apply the L'Hospital's rules. If you don't get the indeterminate form, 0 by 0 form, or infinity over infinity form, maybe plus infinity over plus infinity, or plus infinity over minus infinity, or minus infinity over minus infinity, whatever it is. Infinity over infinity or 0 over 0 form, if you get it, then you can apply the L'Hospital's rules. L'Hospital rule says that limit fx over gx is equal to limit f dash x over g dash x. That means derivative of this function. You calculate the derivative of this function and derivative of the second function, and then you calculate the limit. This will be equal. But there are some conditions. What are the conditions? Limit fx x tends to a should be equal to, if you want to use L'Hospital rules, there are some conditions. First condition is limit fx x tends to a should be equal to limit gx x tends to a should be equal to 0 or plus or minus infinity. Then only you can get this, no? If this goes to 0 and this goes to 0 only, you can get 0 by 0 indeterminate form. Or this has to goes to infinity, plus or minus infinity. Gx has to goes to plus or minus infinity. So individually, this limit, the limit of the numerator should be equal to limit of the denominator should be equal to either 0 or plus or minus infinity. Okay, both should be. If this goes to 0, this also must goes to 0. If this goes to infinity, this also must goes to infinity. This is the first condition. Second condition, derivative must exist. F dash x, comma, g dash x must exist. Must exist. That means these functions should be differentiable functions. The functions are not differentiable in the open interval, the given interval, then we cannot apply this L'Hospital rules. So if you want to use the L'Hospital rules, these two conditions should be satisfied. That is what it says. Function, individually they should go to 0 or plus or minus. If this goes to 0, this also must goes to 0. If this goes to infinity, this also must goes to infinity. And the derivative must exist. That means this exists. Then calculating the limit of this one is same as calculating this one. Okay, proof is given here. Proof is given here. Look at this one. We are taking the LHS fx equal to gx. I am writing this fx over gx by fx minus fa over gx minus fb because we are taking the situation that fa equal to 0, ga equal to 0, because we are assuming that no, as x tends to a, fx equals 0, this equals 0. That means that f of a equals 0, f of b equals 0. We are taking that condition. Okay, we are proving for this part. We are proving for this part. We are not proving for this part. So we are taking this one. So fx minus fb over gx minus 3. I am dividing by x minus a up and down. Then actually this is the definition of derivative f dash x. This is the derivative of g dash x. Okay, g dash x. So this is actually f dash a over g dash a. So we are getting this one. Okay, proof not necessary. Proof not necessary. Just you try to understand this L'Hospital, but you must state this one. Statement is important. All the theorems, statement is important. Mean value theorem and Rolle's theorems are the proof is important. Rolle's theorem, mean value theorem, proof is important. For other theorems, statement is enough. Not proof is not necessary. Right? So let's try to do some examples here. Right. So here it says that note, we can apply L'Hospital rule as many times as required. That means that limit fx over gx x tends to a or something. It can be applied when a tends to any number equal to limit f dash x over g dash x x tends to a. Again equal to limit f double dash x over g double dash x x tends to a. So you can have the derivative any number of times because this is equal to this one, no? So you apply the L'Hospital rule for this one. So that means that second derivative. Again, apply the L'Hospital for this one. Then that is the third derivative. So you can keep differentiate this one. But there's one important condition that. So when you apply, so we can apply L'Hospital rule as many times as required. But before the application of each time, we should check whether the limit in the particular step is giving indeterminate form. So if the limit gives the indeterminate form only, we can apply the L'Hospital rules. Otherwise, you have to stop it. So that is why. So when and how to apply L'Hospital rules, it says clearly. L'Hospital rules should be applied only when fx over gx leads to an indeterminate form. That means you should get 0 by 0 or infinity over infinity form. Then only you can apply this one. Okay, application of L'Hospital rules when limit does not give the indeterminate form throws the wrong result. It gives the wrong result. Okay, wrong results. Say for an example, let's have a simple example. Limit, we want to find sin x over x. X tends to 0. So we know the answer is 1. You all know this answer is 1. But if you apply the L'Hospital rule, it's equal to what? Because you know this is differentiable. If you just substitute, we get 0 by 0 indeterminate form. Therefore, we can apply the L'Hospital rule. So if you differentiate this one, we get limit cos x. Don't use u over v form. Don't use this one. Okay? Just differentiate the numerator. Just differentiate the numerator. Just differentiate the denominator and just put it. If you differentiate x, that is 1. X tends to 0. So this is equal to what? Cos 0 by 1, which is equal to 1. Okay, so that is what L'Hospital. But here they are saying that if the thing is not indeterminate form, then you will get the different answer. Here we have a function limit 3x plus 1 over 2x plus 2. So if you just substitute the value, we get 7 by 6. This is the correct answer. But if you apply the L'Hospital rule, if you differentiate this function, we get 3. Numerator 3x plus 1. If you differentiate that 3, If we differentiate the denominator, that is 2, 3 by 2, which is wrong. Why we are getting wrong answer? Because here, this is not an indeterminate form. This limit is not in indeterminate form. So if you apply the LaHospital rule for indeterminate form, you will definitely get the wrong answer. That is one thing. Second thing, when we apply the LaHospital rule for multiple types, that means I told you we can use the LaHospital rules any number of times. Keep on, you can do it until you get the final answer. But every step, you have to check whether we are getting the indeterminate form. In this step, if you get indeterminate form, then you can carry on the next line, next step. If you don't get indeterminate at the second line, then you have to stop it, right? Look at here. X cube minus 3, x cube minus 1 over x squared plus, I will finish it within 10 minutes. So please give me this 10 minutes. Otherwise, we have to take another session. Please give me 10 minutes. I'm sorry for that. So x cube minus 1 over x squared plus 1. So when you substitute x equal 2 here, okay, when you substitute x equal 2 here, sorry, x equal 1, I'm change this as x equal 1, I'm sorry. Otherwise, we are not getting indeterminate. No? Please change this as 1, x equal 1. I'm sorry. Change this as x equal 1. So if you change x equal 1, then actually, so now what we are doing is, we are differentiating this one. Okay, we are differentiating, this is also 1, this is also 1. So if you differentiate the numerator, we are getting 3x squared. And if you differentiate the denominator, we are getting 2x. So you have to simplify this one. Before you do it next time, you have to simplify this one. So 3x squared over 2x. 3x squared over 2x. Then if you simplify, we are getting 3x by 2. Now if you substitute it here, 3 by 2. It is not an indeterminate form. Therefore, we are getting the final answer. But if you don't substitute, here also same example, 1, 1. So if you don't here you are not substitute, here you are not simplifying. 3x squared over 2x. Again, you are differentiating second derivative. That is 6x by 2. Now you are putting the value x equal 1 here. Then you are getting 6. So this is wrong. That means that here you can't apply this one because this is not an indeterminate form. Non-indeterminate form. Therefore, you can't again differentiate it. So simplifying means you have to check whether at each step we are getting indeterminate form or not. If you don't get indeterminate form at this point, then you just substitute the value and that is the answer. Say for example, here we are not getting indeterminate form. Therefore, now you can stop it here. And if you substitute value x equal 1 here, we are getting 3 by 2. We are getting the correct answer. Okay, so that is how you have to do this one. Do you understand this one, students? Do you understand this one? No. Yes, some people say no, some people say yes. 77, earlier you said no. Which one you didn't understand? 77? Now you understood everything. So there are some questions. We'll do one or two questions and finish it. Okay. So now first question. Limit x equal to 1 minus cos 2x over 1 minus cos 2. Sorry, this should be 0. I am sorry. Change this as 0. Okay. Limit extends, that's typing mistake. Limit extends to 0, 1 minus cos 2x over 0. So if we substitute, actually we are getting 0 by 0. So it's an indeterminate form. Therefore, we can apply the LaHospital rule. LaHospital rules. So LaHospital rule says that, so we have to differentiate. This is equal to limit differentiation of this one. That is differentiation of 1 minus cos 2x over dx over dx over dx. Extends to no change in the limit value. So this is what actually 1 minus cos 2x means. So if you differentiate cos functions, we get 2 times sine 2x over If you differentiate x, we are getting 1. Okay, so limit x tends to 0. Now we put x equals 0, we are getting 0 by 1, so which is equal to 0. Now we are not getting indeterminate form, so we have to stop it. So answer is 0. Right? Right. Answer is 0. So now, do you understand this? Some teachers, they teach these things in A level also without telling this La Hospital rule. They teach this one. Okay. Right. Now we'll discuss one or two problem and we'll finish it. What about the second one? What about the second one? Second one, if you put x equals 0, 3 to the power 0 is 1, 1 minus 1 is 0, 0 by 0. We are getting 0 by 0. So this is now indeterminate form. So how we can do this one? So limit 3 to the power x minus this over x. So how we can write, so we are getting 0 by 0, so we can use the La Hospital rule. So how we can write 3 to the power x? Do you have any way to write 3 to the power x? So if you say 3 to the power x is equal to y, if you say 3 to the power x is equal to y, yeah, e to the power x ln 3, good. So you can write this as e to the power x. So this is equal to limit e to the power x ln 3 minus 1 over x. So if you differentiate this one, that is equal to, using the La Hospital, you have to write it using La Hospital rule. Using La Hospital rule. So you have to check the condition also. Okay, so this is a differentiable function. This is also differentiable function. You have to write that also. So if you differentiate this ln function, e to the power x function, we are getting ln 3 into e to the power x ln 3 minus 0, that is 1 is 0, and this is 1. Limit x tends to 0. Now, if we substitute the value, ln 3, e to the power 0 is 1. So answer is, okay, answer is ln 3. Do you understand this? Tell me whether you understand this. We'll do one more example and finish it, okay? Tell me whether you understand. Right. So last example, we'll discuss this one. Limit x tends to e to the power x, where x tends to minus infinity. Last example. X into e to the power x, where x tends to. Actually, here you may think that we don't have a function fx over gx form. We don't have a function fx over gx form, but you can write it in that form like this. This is equal to limit. Let me write this way: x over e to the power minus x. X tends to minus. Okay, you can write this. Now this is equal to, if you differentiate up and down, we get limit 1 over minus e to the power extends to minus infinity. So what is that? So e to the power minus x, sorry, e to the power minus x limit extends to minus infinity means e to the power plus infinity, no? Is equal to infinity. So here this is equal to 1 over minus infinity, which is equal to 0. Okay, therefore, the limit of this one is equal to okay. Do you understand? Do you understand this? What about others? I think all of you are sleeping. So normally I can uh, find out how many people are really following when I say, okay, lecture is over. Still, some people will remain in the remain as participants. That means that they have just logged in and they went somewhere. So when I end the meeting only, they also end the meeting. So I normally around 30-40 people it happens. Okay. Anyway, it's up to you. I will upload this recording maybe today itself. So please go through. This is the end of your course. This is the end of your course. Please go through this part. Definitely, you will get some question from mean value theorem, Rolle's theorem, and maybe one question from the La Hospital rule. But the theorem is important. You don't need proof. It's not important. One of these proof is one of the proof I will ask definitely. Mean value theorem, Rolle's theorem, one of the proof I will definitely ask. Also, question like this, okay, or question like one of these I will definitely ask for your exam. That will be one question, definitely. So I will take differentiability questions. I will definitely ask some of the things from the last handout. Please go through them carefully because real analysis is a subject where most people fail because they don't really understand the subject. Okay, I have now this time anyway you had online, so you have some opportunity to go back to your previous recording and you go through and try to understand if you haven't understand previously. Okay, so anyway, thank you for giving this time. So this is end of the things. So tomorrow most